food here. Let's start eating it. That's our lag phase. Then once they really start going to town on the food, they'll multiply, and they'll have a long while where they're happily eating and multiplying. At some point, they get populated enough that they really are starting to compete for the amount of food, probably reduce the amount of food that's available, and then you've got competing growth and death rates. That's when you get a stationary phase, and then eventually you have kind of a death phase where you no longer have a net growth or even a stable situation, and your bacteria are dying off because they have no food. Okay, so that's our typical profile if we were to do all this in sort of a batch container. If we consider how to measure biological oxygen demand, we could think about that in terms of doing an experiment like that, letting the bacteria grow, and monitoring what happens to the oxygen in that system. So that's our typical method of determining the BOD in a system, is to monitor oxygen over time as bacteria are growing. We'll get into that a little bit more probably next time or when we come back from break, if not. But you hopefully would have seen BOD at some point in a different class already. Okay, so that means in order to understand about our growth, bacterial growth, this dx dt is what we're going to be interested in, that's mu x. We want to move from just understanding how quickly they're growing to also understanding what's happening to the substrate itself. And okay. By the way, for the recording, it seems like my stream dropped once or twice. Hopefully that's going to be okay. I'll try to figure that out. Make sure it's no issues. Correct this for you real quick. Okay, so we have what we could call the rate of growth. That would be dx dt. We can correlate this to the substrate and have sort of a ds dt. We'll get there in a moment. But we can write this then, if this is our mu, then we can expand that simply and say our growth rate here is equal to x times mu max s divided by ks plus s. So in order to get at how quickly our substrate's being used, we need a yield coefficient. So how much bacteria do we yield per mass of food that they eat? So we're taking a look at the mass of bacteria produced compared to how much food is being consumed. So this yield coefficient y is going to be in milligrams VSS per milligrams BOD. So milligrams of bacteria per milligrams food. Pretty obvious why that would be. And we have a relationship here, and we're going to introduce another constant here, k. And I apologize, it's several k's. I'm following our book's nomenclature, this common nomenclature, so just keep in mind this is lowercase k. This is not the uppercase ks. So just bear that in mind, right? That is not what we're talking about. New k, this is the maximum specific substrate utilization rate coefficient, which sounds a lot like mu max. This is substrate utilization. That's the difference between the maximum specific growth rate coefficient. This is the maximum specific substrate utilization coefficient. So what this is talking about is essentially our yield is going to be related to that maximum specific substrate utilization rate in reference to the maximum specific growth coefficient. And so we can write it as k equals mu max divided by y, or of course we could swap that and say this yield coefficient is equal to maximum specific growth rate coefficient divided by the maximum specific substrate utilization coefficient, lowercase k. So constants all over the place right there. Essentially, we're talking about is when they're growing at, if under the conditions where they grow the best, the yield coefficient is just the one constant divided by the other, the growth divided by the consumption, right? And that holds true even if we're not actually at the max, but we're defining both of these constants as the max that can happen, so it's really not going to deviate from that. So K then is in units of milligrams VSS per milligrams BOD per time. So this will be 1 over time on the top. And down here we have milligrams VSS per milligrams BOD per time. So when we simplify that and solve it, y comes back to that milligrams VSS per milligram BOD. Okay. So, having said all that, we can define our substrate utilization rate. So R, the rate, overall rate for substrate utilization, as the growth rate divided by that yield coefficient. Sorry, trying to write utilization there, but PowerPoint doesn't want me to. Okay, there we go. Okay, so we can define our substrate utilization rate as essentially, I should probably look back here so I'm not crowding you out. Sorry. Could do this actually. Could have done this from day one. So I have the screen here too. So we can define our substrate utilization rate as that growth rate, the negative of the growth rate divided by y. So we're essentially using substrate proportionally to the amount we're growing, except it's a negative. So substrate is going down, and that's also divided by this yield coefficient. So that's a pretty simple way to look at it once we define it properly. Again, our growth rate is described as mu x. That leaves us with one last question about what's our death rate. So we're going to have to balance all of these things to solve problems appropriately for our system. So our death and decay rate would be, we could define as RD. This is going to be negative KD times X. KD is going to be a death and decay rate constant. Of course, this is going to be a decay rate, so that's a negative. So KD, that's per time. As you might expect, it's going to depend on how many are there. So that's pretty obvious, pretty straightforward, and we often will have kind of a typical constant, a lookup table maybe. It'll probably depend a little bit on the type of bacteria, the temperature, some stuff like that. But ultimately, the KD is one of the simpler terms here, but it is also another K. So bear that in mind. So that brings us to a net growth rate, where R prime of G would describe the net amount growing, or net change really, the net growth or decay that we are looking for. So even during this growth phase here, we technically have some death happening, and that's going to be factoring in, but we're growing at such a fast pace, and there's not a particular reason why they're starving at that point, that it's just way outmatched by the growth. So we can define R prime of G as R of G plus R of D. So since the negative is going to be captured within that, it's kind of like the growth minus the death. And we can take a look if we want to and say, remind ourselves that we can define the growth rate in reference to the substrate utilization rate and make a substitution there to get two terms with, essentially we'll end up with two terms that have, we're going to relate the substrate and the x. So we can rewrite R prime of G as negative y times that substrate utilization. Another reason is because we're often tracking the substrate concentration. That's something that we measure, and so that's a kind of a handy tool to use that. Okay, so then that would be minus this KdX. Okay, so from here, what I'd like to do is go through this problem with you. I'll give you a couple minutes to kind of think about and brainstorm how you would approach it, because it's not necessarily, there's a lot involved here, and we've got to remember a few different steps. So I will walk through it with you, but I'm going to give you a few minutes up front to kind of lay the problem out and to get your bearings on it. So go ahead and take a look at that. Essentially, this problem, this example says we've got a shallow pond depicted here. It stays well mixed due to the wind and the steady flow through of a small creek. So essentially, it's well mixed. We've got flow going through, so it should be a CSTR, right? That's kind of how we can model it. We've got a lot of parameters listed here and a microbial kinetics lookup table. Go ahead and just use the default values where needed. That's what our plan is. And then we can solve for, let's see, so it stays well mixed. Oh, sorry, the question asks, and I think that might be on the next page here. So the question's asking if the microbes in the pond consume the inflowing biodegradable organic matter according to typical kinetics. Determine A, the BOD5 leaving the pond, B, the biodegradable organic matter removal efficiency of the pond, and C, the concentration of VSS leaving the pond, so the bacteria concentration. The first bit of the example, the solution is up here. Let me just skip forward. So I'm going to leave it on this page, and then we'll come over to this page and kind of solve together. Almost the whole question, by the way, is visualized here. XF is a question, and SF is the other question, and then efficiency of DOD removal. Okay, so I'm going to leave it here for a couple minutes so you can get a feel. I'll go ahead and read the first part of the solution. It says the pond can be modeled as a steady state CSTR because it's well mixed, and we'll assume that the stream has been flowing at a steady rate and composition for a long period. So the first step would be to set up a mass balance, and it's saying set it up on the microbial mass using the pond as a control volume and the variables we saw a minute ago. Look at this. So let's take a look. We've got essentially the CSTR. We said we wanted to start with a mass balance on the microbial mass. That sounds a little counterintuitive. It is a little counterintuitive in order to know the BOD, but remember that microbial mass is going to be directly tied to the amount of food that's consumed. And so with a system like this, where we have a CSTR with no recycle happening, okay, most of our wastewater systems do have recycle of some sort. In this case, we do not. So it is really just a mass balance on a CSTR with no fancy things attached. The modeling of the two different processes that are going on, the growth of bacteria and the consumption of the substrate, we can get a net balance if we take this approach. So we get Q x naught minus Q x final, I'll just leave it as x, so minus Qx, plus the volume times that net growth rate. So that's going to be, that net growth rate right there has to capture both the growth and decay. And that would be our, technically our mass balance. We can begin simplifying, divide everything by Q. Then another thing that we ought to recognize is x naught was given as 0 right here. So that's going to certainly change this a little bit. So that's going to be just simply minus x plus theta r prime g. And we can go ahead and expand that r prime g out and say this is going to be 0 equals minus x plus theta times the growth, which was mu max s divided by ks plus s times x, and then the decay, theta times the decay, because we have theta there, is just simply going to be kd times x. Now, the other thing you'll note here is that all the terms conveniently have x. So since every term has x in it, we can divide everything by x, and that gets rid of our whole microbe concentration in the first place. So in that manner, we can simplify and say 0 is equal to minus 1. And in fact, I'm just going to go ahead and add that 1 to both sides. We'll say 1 equals theta times mu max s divided by ks plus s minus theta times kd. So from here, we need to solve for s. And we can in terms that we know. So that's quite handy. Takes a little bit of algebra. We're going to have to, let's go ahead and add the theta kd to both sides. So 1 plus theta kd equals theta mu max s divided by ks plus s subscript. And then let's see, we can divide both sides by theta. Probably also want to go ahead and multiply both sides by the ks plus s so that we can get the s out of that term. And so we're close now to having just the system in terms of s. So this part takes a little while, and I think I'll probably give you the equation at the end of this, but really this is specific to cases where you have a CSTR, steady state, the growth and the death, and no recycle. So we're going to do something entirely different for the recycle case. We'll get to that, I think, next time. So anyway, if we continue simplifying, let's see if we can get this done properly. We basically have to expand this system here, and I don't know, maybe I'll leave that theta here. I think that might be simpler, and just leave this part as theta plus KD. Or, excuse me, 1 plus theta KD. Yeah, I think that's a little simpler. So I'm going to leave it like that, and then we'll come up here and say, essentially, to expand it, we've got Ks times 1 plus Ks times theta KD. And so I just did the Ks for both, now the S for both. So it'll be plus S theta KD. All of that equal to mu max times S times theta. Okay, so from here, I'm going to get all of the S terms together on their own. So we'll have Ks, go ahead and factor that out, 1 plus theta KD equals mu max S theta minus S theta KD. So we can factor out S on the right and say this is going to be S times mu max theta minus 1 minus theta KD. And all of that equal to Ks times 1 plus theta KD. So at the end of the day, S is equal to Ks times 1 plus theta KD divided by mu max theta minus 1 minus theta KD. Okay, so lots of algebra deriving from that initial point of a mass balance on X to get us a term for S. Yes, this is technically something that you can and I guess should be able to do. No, I'm not hoping that you would just be able to recognize all that on the fly without kind of being introduced to the topic. And I think that the algebra component of that might be a little bit of a waste of time for an exam problem compared to the real task here is identifying what you need to know and how to get there. All right, so that gives us an equation to use for the problem. So now if we put those numbers in and solve for S, the solution should be .9 milligrams BOD per liter, according to the book's solution here. And so that's using the default value. So it's like KD was 0.06 per day. Got to make sure everything's in days. Need to solve for theta, but we have V and Q, so that's not too big a deal. So we'll have to solve for the different problems or different steps along the way. So, for example, we found KD from the lookup table, 0.06 a day to the minus 1. Theta is V over Q. And it looks like that would be, I think, 4 days. So 200 divided by 50 should be 4. What else? KS was given our typical constants. That's 60 milligrams BOD per liter. And mu max was one more value. That was 3 per day. Yeah. Okay, so that's where all that came from to give this answer. All right, any questions on that? Okay, so we're going to have to do something similar for the part C. To solve for X, we have to solve a mass balance on S. This time we actually know our S value, so as we'll see, it doesn't really matter that our substrate concentration does not factor out of that equation as easily, because we do have an influence substrate concentration. I guess it would be pretty simple if we didn't. So let's take a look at that. Well, first, part B, the removal efficiency. The generic term for efficiency or generic equation should be your initial something minus your final divided by the initial. So that would be S naught minus S divided by S naught, and multiply that by 100%. So that's going to be our 95 minus 6.9 divided by 95. Should give us about 93% removal efficiency. So 92.7. Okay. So part C then, we're taking a look for the concentration of volatile suspended solids leaving the pond. So that's X. Leaving is now the question. All right, so we'll go ahead and set up a mass balance. So 0 equals Q S naught minus QS plus our substrate utilization rate. That's going to be in the volume, we have some RSU. Okay, so take a minute, think about how you might solve that problem. I'm going to remind you here, substrate utilization rate we can define as minus RG divided by Y. All right, so if we, I put up here a couple of reminders about the equations we talked about earlier. Hopefully, kind of putting them together here will start making some sense about why we talked about them and how they work together. So we've got the substrate utilization rate being the negative of the growth rate divided by the yield. The growth rate itself is mu x. We know we have an equation for mu, and our yield coefficient is essentially mu max divided by k. So if we take the RG here, take it negative, so RSU is going to be negative the RG, so negative negative x mu max s divided by ks plus s, all that divided by y, which is, I'll just write mu max divided by lowercase k. If we take that whole term and then simplify a little bit, then one thing we find is the mu maxes cancel, and the k comes up top. So our substrate utilization is going to be negative x k times s divided by ks plus s. And that's what I put here. I guess I kind of framed it slightly different, arranged it differently, but that's what I put in right here. Okay.
Would that be actually
yeah. Sorry. I'm gonna rewrite it so it makes a little more sense with the way I had it there. X K S. Yeah, that's how it should be. Okay. From here, we need to solve for x. And this time, it's a bit simpler. It was kind of complicated up front to figure out how to get the x in there in place. But now that we have it, it's just a bit of algebra from there. So that's kind of the route of substituting the substrate utilization in for the growth so that we can simplify. We know something about the substrate that gives us a handle on how to deal with the growth. Okay, so from there, let's go ahead and add this portion to both sides. So we get xks divided by ks plus s times theta equals s naught minus s, and then simply solve for x. So we'll go ahead and say x times k s, that's lowercase k, uppercase s there, and theta equals s naught minus s times ks plus s. So x then equals s naught minus s times ks plus s divided by k times s times theta. And we can probably, maybe you could simplify from there a little bit, but that's essentially it. That would be our equation for x. And what you see here is we have to have some value of s. So if you were to start this problem kind of from scratch, and you're like, well, we've got two different mass balances going on, two different things that have been asked of us, and you started on one, you encounter the fact that, oh, I need some value of s here in order to solve for x. I don't have that. What do I do? Whereas if you start on the other one, you might be thinking mass balance on s, you'll find s. Well, it turns out kind of the inverse happens a little bit. One we had x cancel in that term, and we could actually solve for s. I think I said that slightly backwards, but you get the point. You could have tried both to get there, but certainly it's a fair bit of effort, and wanted to introduce this concept. We solve for BOD by solving a mass balance on x, and then we solve a mass balance on s to find x. Okay, with the parameters that were given, we could get our final answer here. We put in all the numbers properly, assuming we do all that. And we solve, x should be 43 milligrams VSS per liter. Okay. All right, any questions? All right, so that's all I've got for you today. Next time we'll take up on BOD, activated sludge with recycle, and talk a bit about BOD. All right. I did. So let me grab those real quick. All right, otherwise, I'll see you guys